Okay, everybody, welcome to the webinar focused on MSC Apex Iberian links with specific focus on the automotive industry. As Zanlang mentioned, my name is Steph Evans. I run Evotech CAE in the UK. We are elite partners with MSC Software and involved in promoting and reselling the full range of MSC software products with particular focus on MSC Apex. Which we use extensively in our consulting work. We're involved in online and classroom-based training for the Apex platform and also reselling of the platform into industry. Okay, so with that said, I'll move on with the presentation. Okay, so Apex for the automotive industry. A number of key things with Apex. You may or may not have seen Apex previously. We can achieve massive reductions in model turnaround time with the Apex platform. There are a number of key technology enablers that are very powerful and greatly efficient over legacy tools. And through this presentation, we'll cover a lot of those topics to illustrate some of those in real time. Apex can make the user experience enjoyable. So many companies involved with Apex talk about Apex being almost video game-like in terms of its ease of use, ease of learning. And people can often say it's an addictive environment to work in, and I personally find it very much that way. Apex, in terms of its ease of use and the ease of learning, can open up the analysis process to non-specialists. So these might be more junior engineers or non-FEA or CA specialists, more general or generalist engineers. Therefore, people can get involved in the analysis process much more early on and have their say in terms of product development before you get to the specialist capacity or capability. Apex is available through a very flexible license access through the MSC One licensing system, which gives access to not only MSC Apex but a number of MSC technologies, namely MSC Nastran, Mark and Adams Multibody Dynamics Solver, to name a few. Within Apex, as I mentioned, there are some very powerful FEA and automation techniques built into a flexible architecture. Apex is one of the very few direct modeling geometry engine enabled CA platforms and is also generative in the sense that model changes upstream are flushed all the way back to the beginning, resulting in minimal manual intervention by the user and hence massive time savings in terms of build, solve and post-processing. These capabilities, or the need for an effective CA tool set is very prevalent within the automotive industry, both in terms of getting product to market and also the importance of robust FEA in the development process. And all of that said, Apex gives you, the engineer, the design freedom to develop your current and future products in a manner you have never seen before. And trust me, this has changed the way that we work in our engineering consultancy, and hopefully you will see some of that yourselves. So, the Apex journey. So Apex was first released about 4.5 years ago. Some of the early releases were focused more on the sort of CAD to mesh type stuff with the direct modeling geometry engine that I mentioned. Very easy to use, very fast to build models and very fast to update. We then moved on with subsequent releases to include the Apex structures embedded solver, and that was very useful in terms of running the full design loop or the full analysis loop and making changes, any iterative modifications we need on the structure to ensure integrity. Then we moved into the integrated and revolutionized flavor of Apex, for want of a better term, with some of the later releases again. And the key enabler here was the inclusion of the Python scripting language application programming interface, so the Python API, which effectively means that Apex can be customized and automated almost beyond any boundary in terms of user input and company best practice. So that said, listening to the market, MSC decided that there was a subtle change required and a paradigm shift to enable the latest release, MSC Apex Iberian Links, in terms of its interoperability with MSC Nastran. And we've opened this up with this release. We're calling it a gateway to Nastran, or Apex for Nastran, in the sense that Apex can now write fully functioning model data files out of the Apex environment, be solved externally with Nastran, and then post-processed for result exploration back in the MSC Apex environment. And that's all been achievable with the latest release, Iberian Links, which we'll be focusing on today. In terms of workflow maturity, and I'm sure many of you will be familiar with this, before Apex was around, the legacy approach would be focused on Patran or third-party tools for both pre- and post-processing, wrapped around the sort of core Nastran functionality that's used across many industries and definitely across the automotive industry. As Apex came in, very, very powerful over legacy tool sets in terms of the CAD to mesh type operation, but somewhat limited in terms of the finer points of the nuances of model build in terms of model attribution, loads and boundary conditions, load case setup, that type of thing. So it was used as a companion where it would be focused upstream of Patran or another third-party preprocessor before then the Nastran solve, and then obviously we'd be looking at some of the tool for post-processing. As Apex has developed in maturity, it became a fully functioning preprocessor. So the full model can be built in the Apex environment, certainly for given analysis types, then run in Nastran, but then we were limited to not being able to post-process, so we had to look elsewhere for that activity. But now, with the introduction of Apex for Nastran through the Iberian Links release, we now have the fully functioning preprocessor, Nastran solve, and then fully functioning post-processor for result exploration. Okay, so we'll just talk about some of the functionality growth. So Apex, in its companion mode through some of the early releases, supported a number of Nastran keywords, but was quite limited in terms of analysis support. Once we then moved into additional releases, so we've now got Apex as a fully functioning preprocessor, so we've got more keywords supported, both import and export, and also the ability to set up for a number of different solution types. We then move into the arena where we are now with Apex Iberian Links. So we've got far more mature MSC Nastran keyword support. We've got analysis setup and solution types for external Nastran runs, but also using the embedded Apex structures solver technology. We've also got the ability to explore results through the Nastran external results HDF file format that can be imported into the Apex environment. And we've also introduced at this release the concept of orphan mesh support, whereby we can read in legacy Nastran bulk data information. So we've got no geometry at that level, so we can bring a model in, we can manipulate it, we can modify it, we can generate a hybrid model whereby we bring in some new geometry, and we've got a whole host of different things we can do working on that orphan mesh type scenario. And then of course, as Apex develops, and we've got a number of service pack releases and another major release planned for 2019, all of these functionality groups will grow significantly and further enable the tool set to help you with your efficiency gain and the power of the tool set. Okay, so how can Apex improve your productivity? Apex is now implicit in many MSC Nastran workflows. So we're now at a stage where some of your legacy pre and post processing technology, in simple terms, can be ditched and replaced with Apex to see full advantage in terms of the efficiency gains and ease of use that we've got. Apex is undergoing continual development with every release, both in terms of model build and manipulation, analysis and result exploration. We have, as I mentioned, the Python-based automation environment, so we can automate many aspects, or pretty much all of the aspects of the model build process. But with the advent of Iberian Links, we now can automate analysis and results exploration up front. And this is all enabled through the customizable graphical user interface, and we now have the ability to allow users to create their own tools and forms to almost to their own company specific workflow. Key thing here is that Apex is totally focused, or the development of Apex is totally focused on a desire to address key industry pains. The key thing here that you will be able to experience the full benefit of Apex focused workflows now and in the future. Okay, so with that said, we're going to move on to some demonstrations now, looking at typical automotive industry focused functionality. So the first thing I want to look at, and some of you may know the Apex environment, some of you may be new to this environment, but I just wanted to give you a flavour of the a very simple build, but some of the functionality that we've got. So this video is based around the model build for a suspension assembly. So this geometry has been read in from an external Parasolid CAD source, and we can see some of the key components in here. We've got the knuckle, the upper and lower control arms. So if we focus on the lower control arm first of all, just to illustrate some of the simple yet powerful model build capability we've got. So this is a thin formed structure. So we're just going to mid-surface that structure using the default options in Apex. So we've got a surface that's fully tied together. We've got the shell properties generated by default. We mesh that surface to give us our 2D shell mesh for this type of thin shell structure. And we can now check our element quality. So we get a live feedback in terms of our element quality update. And we can see we've got a number of invalid elements. So we've got some very thin faceted surfaces. So we're going to just use some of the geometry manipulation tools. And again, Apex being generative, the geometry is tied to the mesh, which is in turn tied to the property, and also the element quality in this case. So as we make these changes, we update the geometry and the mesh, and the poorly shaped elements disappear from view, and we've removed them from this part within the master assembly. There's a number of ways of doing this, but this is just illustrative of the generative nature of Apex. So if we now view the resultant mesh, we can now check things like the resultant shell thickness. So we haven't had to re-attribute properties. They're all tied through again through the generative nature. So minimal mouse clicks, big time savings potentially for more complex models. Verifying element normals. And then one key thing that we have within the Apex environment is the ability to run the Apex structure solver. Now this could be for production level output, but in this case we're using it for a simple verification run, just to make sure that this part of the model is tied together and is working as a true FEA description of the part we're trying to represent. So we're just running a simple normal modes analysis. This takes us through into the post-processing environment, and then we can look at the table of modes and the frequencies that are developed, and just look at the mode shapes just to ensure that they make sense and the structure's tied together. So obviously this is a free normal modes analysis, so the first 6 mode shapes are rigid body. So once we've built all the parts and verified them within the assembly, we can bring them all together. This full model process with static load output took less than an hour, so we have very good efficiencies in there. So some areas of the model where we've got parts which will be welded in reality, we're just going to idealize that connection with a glue contact meshless technique just to fasten 2 parts together. We've got the concept of joints, which are new to the Iberian Links release, and this allows us to specify many different types of joints. So we're going to specify a revolute joint, which is representative of a pin and a shaft with a bearing connecting these 2 parts together. So we just specify the 2 end, or the end curves connecting the red shell component or the pinky shell component into the face of the blue detailed mesh component, and middle mouse button to accept. We can modify the position and the orientation if necessary, but these are concentric holes, so we're good to go with the good quality geometry. So we can look at the joint definition. We have it in the model browser tree. Once we've got that defined, we're just going to illustrate here again some of the generative nature of Apex. So we're going to remesh the knuckle, the solid mesh knuckle in this suspension assembly. So as that mesh is updated, the joint is updated as well. So the generative nature of Apex has flushed those joint connections through to the newly defined model. Running a normal modes analysis, just again as a verification, we can see how those revolute joints are working and that the structure is all tied together and behaves as it should for a structure of this sort. Again, just a quick strain energy plot to show where the peak loads may well develop from a dynamic load case. So we're now going to run, just for illustration, a simple load case, a simple static load case, linear static. So we've got a number of constraints and a symmetry boundary condition. Again, very straightforward to define this in Apex. And then a very quick response, both in terms of the shell and solid stress output. We're just looking at von Mises for the lower control arm, just as an illustration of what we can do with Apex. So again, just an overview. Took less than an hour to build that complete assembly, so hopefully some idea of the efficiency gains that we can see, and obviously we can take that on to more involved models at your leisure, really. Okay, so looking specifically now at how Apex interacts with MSC Nastran. So Apex can be fundamental to your current and future MSC Nastran. I'd probably caveat that to say that Apex is fundamental to your Nastran-based workflows. In the sense that we have now enhanced MSC Nastran keyword support for both model import and export, and the bulk of this is obviously default Apex behavior. Obviously with the Python enabled automation environment, we can extend that almost on a company by company basis. We've got the ability to interrogate results through the attachment of the MSC Nastran, the new format, the HDF5 result format. Well, I say new, it's been in industry for a number of years now, but we can take advantage of the powerful result exploration and automation capabilities within Apex. And then this simple infographic just shows on the left hand side the number of supported BDF keywords which are both imported and exported, or can be imported and exported from the Apex environment, across coordinate frames, multi-point constraints, materials and properties, model definition, and loads and boundary conditions. Obviously, we're looking for the red bars, one of the early Apex releases, Diamond Python, and now the grey bars show Iberian Lynx, and we've got a massive increase in the number of supported keywords. On the right hand side, I didn't really want to bore anybody with table after table of supported keywords. This is just a word cloud that shows some of the range and breadth of keyword that is supported within the Apex environment. Okay, so look specifically at the MSC Nastran workflow. This is for a slightly more involved model now. So we've got a chassis model with, I don't know, maybe 120 discrete parts in it. And this is brought in from I think this came in as a CATIA assembly. So we've got the original solids. We've been through some mid-surfacing operations, and again, very straightforward, using the direct modeling geometry engine in Apex to do this. We can look at the resultant mesh. So we've got a reasonable mesh distribution for global stiffness and strength cases. We can look at the shell properties that have been defined by default as part of the mid-surfacing. And then one aspect that we touched on earlier is the ability to do a meshless connection using glued contact. And this is prevalent throughout many aspects of Apex. So that showed the glued contact, which in fact is a series of explicit MPCs under the hood, as it were. And we look at the glued contact on the sub-assembly level as well, for one of these cross braces, and see how the model is tied together. And of course, we could run a verification load case or normal modes load case at any level within the model. We're just doing a quick check here on element quality. We could check all sorts of things, free edges, element normals, that type of thing. So once the model is built, we can just look through, apply a number of constraints and some force and moments into the structure. So again, a very simple load case, but just illustrative of the type of stuff that we can now do within Apex. So once we have the model built, we can now what we call place in analysis scene. So that effectively becomes the target for the model, and we can specify that we want to create a scenario. So that's a single or a series of load cases, and we've got full control over that definition. And once we've got that, we can export the Nastran data. We can set the units. We can specify whether we want to export a single file or a multiple include file basis. And once we've run the Nastran job, obviously skip the step here. We can then read the Nastran result file back into the Apex environment, go into post-processing, and then we've got full control over the sort of contemporary result exploration tools that are available in the Apex environment. So just a very quick fringe plot, animated fringe plots looking at von Mises stress across the shell elements. So pretty straightforward, simple structure, but again, very quick to build and verify and get production level results out. Okay, so the next quick demonstration we're going to look at is the concept of the orphan mesh workflow, again for this chassis model. So just to reiterate, orphan mesh is when you work from the source bulk data file, maybe a legacy Nastran model. You perhaps don't have any CAD to support the full model build, but once that geometry is read in, you can manipulate the mesh to remesh, regenerate, modify at your leisure, really. So we're specifying the import of the original bulk data file for this chassis model we just looked at. We can specify the unit system. We can specify how we want to organize the model. So we're importing this model as a series of contiguous mesh parts. So each discrete mesh has its own part within the subassembly, and that obviously makes it very easy to manage from the model browser tree perspective. So we can see some of the local detail as we looked at previously. So left-hand side now, as we click on those entities, we can highlight them in the model browser tree. And what we're going to do is convert that mesh, the orphan mesh that was read in, into a series of faceted surfaces, so into a series of geometric entities. As we do this, the shell properties that are used to populate those surfaces are stored internally, and we are now in the position where we can remesh, modify this geometry to give us the structure that we want to see. So bringing the original mesh back into view and then highlighting those meshed entities that we've used to generate faceted surfaces within the model browser tree, we can now delete those original meshes. They're no longer required. They're surplus to what we need to do. And we're left again with faceted surfaces, as you can see in the browser tree, and these surfaces can be exported to CAD if necessary. So once we've got those faceted surfaces created, the original mesh removed, we're going to modify them. We've just got some simple operation here. We've created some cylinders which we're going to subtract from those original surfaces using a Boolean operation, again using some of the very powerful direct modeling geometry tools. Remesh those faceted surfaces. So those surfaces now are populated with the original shell property. We can modify those if necessary. Bring them back into view, bring the full model back into view. We're going to use the glued contact to tie this all together. Again, single sweep based on the glue pair tolerance, and we're good to go in terms of our analysis. So we're solving this in terms of or using the Apex Structures Embedded Solver, and again we can now see the resultant deformation, obviously massively amplified. So we're just going to change the scaling for the deformation plot, bring it into view to make more sense. So we've got 10 times true scale at the moment. We can animate at that level. Obviously this is a linear static analysis, so we wouldn't want to go too high into our displacements. And we can look at our von Mises stresses and the influence that our orphan mesh modification has had on that overall structure. So we're good to go there. This is a second example where we're tying orphan mesh geometry, so remeshed entities in the blue and green regions, with some imported CAD for the the orange upper and lower plates. We've glued the fine mesh to the coarse mesh, and we've defined a series of connectors to give us our true fastener definition at the joints if we wanted to extract joint loads or fatigue loading around those joint regions. So very powerful techniques for that orphan mesh type workflow. Adams is very prevalent as a multi-body dynamics tool within CAE, and especially in the automotive industry. So Apex can now be used very nicely with your MSC Adams multi-body dynamics workflow, with the ability to generate valid or quality FEA models using some of the Apex analysis readiness tools for subsequent modal neutral file MNF generation. So what we're doing here is effectively defining what we call the flexible bodies for inclusion in a downstream Adams multi-body dynamics analysis, and Apex can help us with that. So once we've got the geometry and the model built, we can create the interface points within the Apex environment, and these will act as the external connection points within the Adams analysis. Again, very straightforward to do that. We can verify the flexible body modes using Apex, so the Apex Structures Embedded Solver. And once we've got those modes, we can generate the modal neutral file or files as an output from a normal modes analysis, and then export them with minimal user input from Apex directly into Adams for subsequent downstream work. So just to illustrate how that could work within Adams, so opening up the Adams environment, and some of you may or may not be familiar with Adams itself, but we start Adams, we specify for the bodies within a given assembly. So I should add that as we start, these bodies within the suspension assembly are all rigid body, so it's just a plain kinematic study. But we're going to make some of these entities flexible. So we go into the make flexible options within Adams. We can open Apex. This can be scripted to work automatically behind the scenes. Open the geometry and its attachment points, or their attachment points, I should say, and then generate the modal neutral file or a Nastran bulk data file. So if your Apex process is to support Adams and Nastran, then you'd obviously create a Nastran bulk data file. If this is solely for an Adams workflow, then you'd create the MNF directly within the Apex environment. Once that data type is available, we go back into Adams, into the make flexible form, and then we can either read the MNF file in directly or execute Nastran to generate the MNF file explicitly in its own right, and then associate the MNF file with the assembly we're working with. So we're swapping a rigid body for a flexible body, and then bringing that in, and now the component is treated as a true flexible body based on the MNF definition, and Adams now becomes a true flexible simulation multi-body dynamics environment. Okay, so one thing that's come up with a number of the webinars that we're looking at, we've actually repeated a similar webinar for the aerospace, the shipbuilding, and the large fabricated structure industries. And this is prevalent for the automotive industry as well, is how is Apex at handling welded structures? Well, there are many different ways of tying models together within the Apex environment, and Evotech, the company that I'm involved with, we've developed a 25-minute tutorial all focused around Apex, looking at different techniques. So we've got weld simulation techniques such as nominal stress, hotspot stress, and effective notch stress methods. And I would direct you to have a look at the evotechcae.com website, where we've got a number of these and related tutorials that could well be of interest to yourselves. If necessary, these links can be distributed after the webinar directly. Okay, so a bit more on weld analysis. So this is some work that's been done by a partner company, and they're focusing Apex again on a different workflow again. This is to use another MSC technology, Simufact welding, whereby the model is built and then prepared for external analysis within Simufact. So this script runs with marginal user input, mainly to populate or to answer any questions that pop up from the script, and then works with the geometry and builds the model. So I'll just play this demo, and you'll get the gist of what's going on. So again, using the Python API environment, we're going to run a script. So first of all, we specify the CAD file that we want to work with. So a parasolid file in this case. We specify some spot weld locations from a CSV file. We specify the radius of those spot welds. Those are generated automatically within the Apex environment using the script, and the overlying CAD is brought in. So you can see here we've got the smaller pinky orangey region that's going to be spot welded to the larger bonnet region or floor pan region, wherever it is. So Apex is running, and if you can see in the top right hand corner, it's running through the instructions. So we're splitting surfaces based on those weld locations, meshing both the smaller and the larger regions, just running through, obviously no user input to do this. It's a pretty detailed model, so it does take a few seconds to run through, but we can now see the resultant mesh. We get a message that the script is run appropriately. So we can see now if we hide the spot weld locations, and we can see the Simufact welding zonal definition for external analysis. So that will be read out and then post-processed or analysed and post-processed in the Simufact environment. Okay, so just would like to say that that video was kindly provided by colleague Fernando Okigami of technicaca.com, based in Brazil. Okay, so that pretty much covers specifics for the automotive industry. We're just going to look at some enhancements that have come in through Iberian Links. These will be new for anybody, especially people who haven't seen Apex before, but just to give a flavour of some of the developments that have gone on. We now have a number of geometry enhancements, so we're pretty much, or pretty close to a fully functioning CAD type system in terms of the geometry creation and manipulation within the Apex direct modeling geometry engine. So we now have revolve, extrude, sweep, and lofting, and this simple model just demonstrates some of those techniques. So we have this kayak structure, or simple series of surfaces. So we're going to loft a surface, so that involves selecting non-connected edges, and then the surface will be lofted across those connected, those discrete edges as we select them. So we get a visual update of what the surface is going to look like, and once we're happy with those, middle mouse button to accept, and the surface is generated as we wish. And again, we've got tangency controls at all levels to control what we do here. Just looking quickly at an example of sweeping within the Apex environment. So we've got a curve that's going to represent the stiffener for the resultant kayak. So we're going to sweep that curve around the surface edges that we can see on screen now, and then we're also going to pick the surface faces to give us a sort of projection and normal direction, and we see a preview of that surface, middle mouse button to accept, and we've now got the full surface defined as required. We've split the kayak based on the intersection of those surfaces, and then we can bring in the new geometry to suit and show how that sits together. We've got geometry from mesh, and we touched on this with some of the orphan mesh process, but we've got a quick example here of a machined component you may see in a typical structure. So bringing the orphan mesh in, we've brought some geometry in that represents a portion where we want some detailed solid mesh grafted into the shell mesh. So we're going to delete the shell elements in the region where we no longer need them. Delete the geometry from view, and we can see there's a hole in the shell geometry. And we're now going to use the geometry tools to create a faceted surface from that underlying mesh. And again, it's created the surfaces. This would work for flat, curved, or even doubly curved spherical type geometry. It's remembered the underlying shell thicknesses. We can delete the original mesh, and we can now remesh and manipulate that geometry to give us any modification that we want. So here we may choose to seed an edge just to locally redefine what's going on, just as an example, but we could move edges around, that type of thing. And again, we've got the shell properties maintained. Bringing the 3D mesh back into view that we've tech meshed in this case, so maybe we want to get some fatigue features at some of those machinings, and then we can glue the solid into the shell to give us the overall load transfer across the interface. And again, a very quick and robust tool to develop that kind of model. Okay, so some of the Iberian Links meshing enhancements. So hex meshing. So Apex has, for a number of releases, a very, very strong hex meshing capability. We now have the ability to diagnose some hex meshing potential workflows that we may see for typical structures. So this is a simple machine or casting that we've got. We're going to partition the solid to make it hex meshable and use the standard hex meshing tool to develop those 3D elements. We've got some problems with element quality, so we're going to seed the faces using a 2D shell mesh dominated by quad elements and nicely formed quad elements. But when we mesh this spigot region with quads, we see that the fillet appears in yellow indicating a Hex Mesh potential problem. So we can see there's a mismatch in the meshability, the seed across those edges. So very quickly we can update that seed, go back into the Hex Mesh tool. The Hex Mesh now follows the seeded surface, and we've got very good quality in terms of the underlying Hex Mesh that's developed. We've got enhancements in edge tie. So again, edge ties are means of tying edges across parts contained within an assembly where we don't perhaps want to equivalence nodes. And we can see here, going back to the kayak model, so we're maintaining two discrete parts within the assembly, and we've actually got a free edge between them at the moment. So we're going to use the edge tie technology to tie them together. So this actually creates a series of zero length R bars which are snapped together to give us a consistent nodal connection at those interfaces. We can look at the edge ties and check the free edges. By respecting the edge tie, we can now see that the structure's tied together fully. Now, one thing that's coming new with the Iberian Links release is that we now have the ability to transform meshed models or FE models, and it will take the edge ties with it. So we're just mirroring this quarter model into the full kayak form. So just specifying which entities we want to mirror, specify the mirror plane, and again, we're getting good visual feedback here in terms of what Apex is about to do. So we're just rotating the mirror plane by 90 degrees. It gives us the update that we want, middle mouse button to accept, and very quick means of bringing that model into position and tying everything together. And if we look at the edge ties explicitly, we can see that they've been copied as well as the full structure. And we can see the nodal connectivity at that level. So once we've got that, we could potentially run a just look at the free edges and then run a verification load case to show that we've got things tied together as they should be. So almost a trivial approach now to build a fairly complex model. Massive time savings as we talk about with Apex. We've got some advances in some of the surface meshing technology, the introduction of what we call the incremental surface meshing tool, and also the ability to orient or modify the XY orientation for a given shell element. So obviously we can control shell normals, but now we can specify the angle or make parallel with a given edge the X direction of a shell element, which is useful for post-processing in some instances. So a quick video to illustrate this. So we've got a simple panel with some holes in it. The original surface mesher defines washer features around all the holes, but on this bottom hole, it's too close to the edge, so it doesn't give us what we want. With the advent of the incremental surface mesher, we can see how those entities, or how that feature needs to be modified. So we're going to change the width of the washer that we're using, and then we can go back in and remesh mesh the full structure, and we've now got a washer that fits in the geometry as we require. The shell XY orientation, so we're changing the way the local coordinate frame is working for a given shell element. So we can do this on an element by element basis. So that corner element we're swapping to point parallel with the short edge of the plate, or we can specify all of the elements to align with the short edge of the plate. And again, this is useful for post-processing in some instances. So that's now available within the Apex environment. We've got a number of Nastran interoperability enhancements. So we've got better control now of ID management within the model, so we can specify starting ID and the ID range for nodes and elements. We've got the ability to create explicit coordinate frames, whether they're rectangular, cylindrical or spherical, based on manual input of the position, and of course that can be automated using, well, all of this stuff can be automated using the Python automation environment. And we've now got the ability to explicitly create discrete ties. So for the Nastran literate, discrete ties are RBE2 and RBE3 entity types within the Apex environment. So a quick example of how that would work. So we brought in this model. We've got a hex mesh of the bracket and a single beam mesh for the tube. So we're going to create manage some of the element node IDs for the bracket. So specify the starting ID, specify the part we want to modify, accept the defaults, and then if we look in the exported Nastran bulk data file, we can see both the element and the grid starts with that numbering sequence. We can create coordinate frames explicitly, so we're creating a cylindrical coordinate frame at the center of this geometry. The concept of apex magic marker, so we pick an edge and it automatically highlights the center of that edge. So for an arc like this is very, very useful. We can use those local coordinate frames to specify lots of things. In this case we're going to look at a boundary condition. So we have internal faces of this structure, respecting that cylindrical coordinate frame, and create the boundary condition accordingly. Now we're going to use a discrete tie. So this is a compliant tie, which in Nastran terms is an RBE3. So we're going to tie the internal faces of that geometry to the bar element that represents the tube. And again, single click. This is all fully generative, so any mesh updates would be flow through to the rest of the model. We've got a very nice form access for manipulating discrete ties and modifying them. Much better than any legacy tools that I've ever seen. We can post-process using the local coordinate frame. So we're looking at the R, theta, and Z displacements as vectors. So a number of improvements there or enhancements to allow you to work with Nastran data in a more transparent manner. We've now introduced the concept of joints into the Apex environment, and this works with an underlying MSC Nastran card definition. But basically, if we've got discrete parts that we want to connect using a joint definition, so we perhaps have some rotation release or something like that. So we've got revolute joints, spherical joints, that type of thing. So here we're going to create a revolute joint between the board surfaces of the pink member, and then we're going to connect those to the 1D end of the blue entity, and we've got the joint definition generated, and we can see that in the model browser tree. And if we were to write the model out, we would see the intricacies of how that's being defined in terms of the Nastran deck. So we've got local coordinate frames, grids, RBEs, etc., etc. So again, a massive efficiency gain in terms of the way that we can work with this type of data. Result exploration within Apex. So obviously we've got the ability to import and interrogate output from the Nastran HDF5 result file. We've got the ability now to probe 0D, so that could be nodes and elements or joints or fasteners, connection using the 0D probe, and we've got the 1D probe where we can effectively draw a path along a surface or potentially through a solid thickness and look at the results along that path, and then we'll get graphical output in terms of XY coordinates in the Apex environment. We've got the ability now where we can write results to an external CSV format. This is new to the Apex environment, so again, all of this stuff can be automated using the Python automation tools available to us. So a quick example here. So we've got a sort of crane type structure. We're going to export the bulk data file. We can look at the Nastran deck. We can even modify that at that level if necessary. We're going to run the Nastran analysis and then read the H5 file back into the Apex environment, importing the Nastran results, selecting the file we want to work with, and then we're back into the Apex post-processing environment to allow us to explore the results of the model we've generated. So just a quick deformation plot here. So we're just going to bring out, just to show some of the probing tools. So we're looking at some of the 1D stresses for the bar elements representing one of the simplified booms. And then when we've got those, we can see the stresses at a stress recovery point, one of the corners. And we can use the probe tool to send the probe data to a data grid. We can manipulate the grid at this level. We can sort, we can remove, we can even modify the numbers if we wanted to do that. And then read the results out to CSV formats for external post-processing. So again, opening up the capability of Apex all the time with this Siberian Links release. We've got some enhancements in terms of customization and automation. So the scripting API or the Python API is now fully functioning in terms of analysis and results exploration. Previously, it only supported model build, but we've now got a capability to automate the whole process. We've got the ability to customize the graphical user interface through the ability to create user-defined forms and link those to scripts that would run behind the scene. So a quick example here, this is a parametric macro we've got developed to look at buckling response of a simple plate. But again, the thing I'm trying to illustrate here is the fact that the script is running model build, result solver, and the results post-processing as well, all in a single environment. So we've effectively black boxed, for want of a better term, the whole process. So there's no user input, whatever. So this has significant benefit in terms of company workflow. If you wanted to farm out some of this work to or to improve the efficiency of this type of work with non-specialist engineers. So we can look at the result. This is just a linear buckling analysis. So we can look at some of the mode shapes, and we actually, when we plot a table of the resultant buckling factors, we can see that we have an instability problem, buckling factor less than 1 for a couple of the mode shapes, and we could rerun the analysis to improve those if necessary. Second example now, looking at how we can modify the graphical user interface through the custom tool palette. So this is a script that was developed by a colleague in the States, Larry Pierce, so big thank you to Larry. We've got in the custom tool palette a capability of flexible hose, so the model definition in terms of dimensions, thicknesses, material properties, that type of thing is fully defined in the form. So one would populate the form as required and then simply run the script. The model is built to those geometric dimensions, ready for, the meshing takes place as well, full attribution, and the model's ready to go in terms of analysis and subsequent post-processing. So again, big capability improvement in terms of, huge efficiency gains could be achieved with this type of thing for your company workflows. Okay, so that pretty much covers the slides I wanted to take you through today. People talk about tool sets being game changers. My personal view, and that's how many people that I've worked with in the industry, that Apex is now at a level to really be a game changer in terms of the ability to generate models quickly, to verify them quickly, and to introduce huge efficiency gains, and really taking a lot of the pain and lead time out of the analysis process, thus enabling massive benefits for you and your companies. Okay, thank you.